Still talking about one of the subtleties of friction here. I want to talk about Bernoulli's principle. Again, this is in section 2.4 of your textbook. Bernoulli's principle, sometimes you'll hear this referred to as the Magnus Effect. Bernoulli's principle is responsible for a lot of things. The Magnus Effect generally is applied to curving, like a ball that's thrown or kicked or something. So if I throw a baseball and it's a baseball pitcher throwing a curve ball, that's the Magnus Effect. Or you hear it a lot with soccer players. When a soccer player does a free kick and there's like the wall of defenders in the way, they can kind of curve the ball around the wall of defenders. That's often referred to as the Magnus Effect. It's just part of Bernoulli's principle. Bernoulli's principle says this: when a fluid speed is low, the pressure that fluid experiences is high, and when the fluid speed is high, the pressure of that fluid is low. So they kind of go opposite to each other. Just quickly, a fluid is any liquid or gas. So air is a fluid, water is a fluid, honey is a fluid, carbon dioxide is a fluid. Anything that's a liquid or a gas is a fluid. There are a few weird solids that sometimes are semi-solids that can be considered fluids, but we're not going to look at those. When we're talking about this then, the curve ball, so let's talk through the curve ball a little bit. Imagine here's my baseball. My baseball, like we're showing here, I've got this direction of flight. So here's the direction of flight. The baseball is being thrown forwards. We can imagine it's like the air molecules are flowing this way around the baseball. Okay, so I know it's the baseball moving forward, but you could kind of say from the ball's perspective, it's like there's a wind in your face. It's like if you're in your car driving and you roll down the window, it feels like this wind blowing towards you. That's what the baseball experiences. If the baseball is also spinning, okay, so as it moves forward, I also put a spin on this ball, so it's kind of moving forwards and rotating like this. What that means is the baseball, as it kind of goes around this way, you can kind of see over here, there's like these seams in the baseball. There's friction between the surface of the ball and those air molecules. The friction here, because the ball is moving in the opposite direction to those air molecules, this friction is actually going to slow those air molecules down. So as the air molecules, you can picture like little, spheres as they kind of go, as they rub across the surface, they're going to go slower. And slow is a relative term, but they're going to go slower relative to the opposite side. On the opposite side here, the ball here is kind of spinning in the direction of these little air molecules. That's going to speed them up. So the air molecules on this side are going to go faster. Okay, so relative to each other, I get slower air movement and faster air movement. That's because of the friction between the ball and those air molecules. From Bernoulli's principle, what we know is wherever the fluid speed is high, pressure is going to be low. And wherever fluid speed is low or slow, pressure is going to be high. Okay, so that's what Bernoulli's principle says. That's kind of the end of Bernoulli's principle. But there's more effect from this because we kind of know from, I don't know from where, just in general, we know that fluids move from areas of high pressure to low pressure. Okay, so if you picture like a balloon, you blow up a balloon. Here's this little rubber end here. And as long as you hold it, the air stays in there, but it's under high pressure. If you open this opening, this air is all gonna rush out because it moves from high pressure to low pressure. Same thing here. The air is gonna move from high pressure towards low pressure. That's gonna put a force on the ball. Okay, so there's a force. I don't know if I can write this anywhere here, force. That puts a force on the ball. The air molecules here are trying to get over here. That's going to start to push the ball, and that's going to make it not fly in a straight line. It's going to start to bend and curve in its path. Okay, so that's how you can throw a curveball in baseball. That's how you could kick a curveball in soccer ball. You could make a soccer ball curve. This happens in other sports as well. There's lots of sports and stuff that do this. There's other places where we use this effect, and one of them is in flying. Okay, so an airplane wing, that's not the greatest drawing, but airplane wing looks something like this if you view it from kind of the tip of the airplane wing, if you view edge on. So imagine the airplane is kind of back here, it's going forwards in this direction. We're seeing like the tip of the airplane wing kind of coming out towards us. So the airplane wing is moving forward. Again, that's like air molecules are moving sort of across the surface of the airplane and they're coming back here. I'll draw a few paths. Here's my air molecules moving around. This is an airplane wing. What you can imagine then is, let's say there's two air molecules right here side by side. really they're at rest, and it's the airplane wing kind of slicing between them. So imagine here's two air molecules. Let's let the pen here, or my pencil will be my wing. As it slices between them, it's going to shove those air molecules apart, and as it goes through, they're going to kind of come back together because there's like a bit of a vacuum behind the airplane wing. So the air molecules are going to go up and around and come back together on the other side. But because of the shape of the wing, the top one, the one that goes over the top surface of the wing, travels a further path. Because it's traveling a bigger path, you could think it has to kind of get out of the way faster as this airplane wing rams through it, or imagine it travels a greater distance. What that means is we're going to get a faster speed, fluid speed on top, and a slower, let's say faster and slower, slower fluid speed on the bottom. What that results in then, again, from Bernoulli's principle, slow speed or low speed means pressure is high. Here, pressure is low. Again, high pressure air wants to get to low pressure air. That puts a force on the wing going up. And again, if this is an airplane, you know that gravity is pulling it down. So originally we need a lot of this force, this lift force, people sometimes call it. We need a lot of lift force in order to get the plane up off the ground. Once it's flying in level flight, we just need this force to equal this force so that the plane flies a nice level flight. It doesn't accelerate up or down. So there's a couple of applications of Bernoulli's principle. There are lots more. There's a couple in the textbook. We'll run through some either online or in class. But Bernoulli's principle is cool.